Hey guys, welcome back to my channel. In this video, we'll talk about depth first search. Let's start with the prompt first. Thousands of airplanes travel around the world every day, connecting one city with another. Let's consider only 10 cities to make things simple for now. Let's assume that there is a direct flight from Sydney to Shanghai. There is also another direct flight from Sydney to Kathmandu. Similarly, I'm going to assume flights from all listed cities that connects other cities listed below. Given any two cities A and B, how would you find if it's possible to travel from city A to city B? For example, is it possible to travel from Sydney to Hamburg? Yes, it is, because you can go from Sydney to Kathmandu, Kathmandu to Dubai, and from Dubai to Hamburg. How about from Mumbai to Prince George? No, there is no way you can get from Mumbai to Prince George. No matter how many cities you jump from Mumbai, you'll never reach Prince George. Let's see how we can solve this problem by applying the basics of graph theory. Before we start, let's learn some terms relevant to this problem from graph theory. The 10 cities given in the problem are known as vertex or nodes in the graph. The yellow lines connecting different cities are called edges. If you notice, there aren't any arrows in the edges of the graph. This type of graph is called undirected graph. In undirected graph, you can travel from A to B and from B to A as well. For example, you can take flight from Mumbai to Sao Paulo, and you can also take flight from Sao Paulo to Mumbai. We can clearly see that there are two independent graphs here. One is on this side and the other one is on this side. These independent graphs are known as connected components in graph. That means this problem statement has two connected components. Now, the intuitive way to solve this problem would be to use hash maps. We'll discuss about that in some other video. Another way to solve this problem would be to use either DFS, depth first search, or BFS, breadth first search. BFS would be a better way to solve this problem, but in this video we're going to make use of DFS. And in the later video, we'll use BFS to solve the same problem. To simplify the graph even further, I'm going to assign unique ID to each city or vertex and replace city names with those ID. Using numbers gives us greater flexibility in terms of calculation, and it also makes it a lot easier to code. Later on, we can make use of simple hash table to retrieve the original city names. Let's start by creating a data structure for this problem. We have 10 cities. For now, I'm going to explicitly write 10 here. Later on, when we solve this problem, we can work on generalizing it so that it works for any number of given cities. This problem has two important sections. One is definitely the DFS algorithm, and the other one is this line, the data structure for this problem. We're trying to create an adjacency list to store our data. This is one of the several data structures to store the graph data. This is what we have created until now in computer memory. Let's move on. It will be more clear when we start adding data in our list. Let's bring back our graph network to fill up the data. We can see that there is a direct flight from 0 to 1, so we can write something like this. But this is an undirected graph, meaning you can also take flight from 1 to 0. So we can reverse these numbers to connect it the other way. Again, there is a direct flight from 0 to 2 as well. We are going to connect 0 and 2 exactly the way we connected 0 and 1. In this way, I'm going to let the animation run until we fill all the data. We have successfully created our data structure and stored our data. Now it's the time to apply DFS. Let's understand the algorithm first before we apply it. Let's say we want to find out if it's possible to travel from 0 to 6. We can clearly see that it's possible. The challenge is, how can we make computers see it? Here's how the algorithm works. We start from one of the two vertices. Let's start from 0. Once we visit, we will mark it in red color and explore all of its connected vertices. Vertex 0 has 3 other connected vertices. Connected vertices are also called its neighbors. Let's go to the first one. Before jumping to vertex 1, we first check if this vertex is red in color. We will only jump if the vertex is not in red color. When we go to vertex 1, we mark it with red and explore all of its connected vertices. Vertex 1 has only one connected vertex, that is 0. Now we see if 0 is red in color. It is, so we don't jump there. There are no more connected vertex left in 1. We go back to explore another vertex of 0, as we haven't completed exploring all the neighbors of 0. So next neighbor of 0 is 2. 2 is not red in color, so we color it in red and explore its neighbors. First one is 0, which is already red in color, so we see the other neighbor, which is 4. So we mark it in red color and explore its neighbor. 2 is already red, so we jump to 5. We mark 5 in red and then explore its neighbors. 4 is already red, so we jump to 3. Mark it in red. Notice both the neighbors of 3 are red. So we go back to 5 because that is where we came from to this vertex. The only remaining vertex here is now 6. This is our destination vertex, which proves that it is a path from 0 to 6. One of the ways to achieve this is by implementing simple recursive function. Let's move to write an algorithm for the same. We'll come back to the main function later. Let's create a function called isFlight, which takes 4 arguments. First argument takes the graph data. Second is the total number of cities. Third one is the starting city. Fourth one is destination city. And finally, the fifth argument is for storing the list of cities that we have visited. First thing we do inside this function is mark the city as visited as soon as we enter inside this function. And then we check for all the neighboring cities of whichever city we are currently at. We create a variable called neighbor. One variable is enough because this for loop runs for all the neighboring cities. If the neighboring city is our destination, we return true, else we need to jump to that city to explore its neighbors. But before that, we need to check if the city is already visited or not. This is where we call the function itself, and this time our source will be the neighbor. If any function returns true, then we exit with true, else we return false. This algorithm should be able to give us if it's possible to move from one city to another. Let's go back to our main function and call the function. Here we first need to create an array to store the list of visited city. Let's call the function to check if it's possible to travel from city 0 to city 6. It's possible. This is how recursive DFS algorithm works. Thank you so much for watching this video. If you want me to make more similar kind of videos in the future, do let me know in the comment section below. And don't forget to subscribe to my channel.